Good afternoon and welcome everybody from my side to the Trinity College Open Day. I'm Wojciech Kusic. I'm head of the Nanoelectronics and Spintonics groups in the School of Physics and also principal investigator at the Center for Research on Adaptive Nanostructures and Nanodevices. And what I want to talk to you about today is this famous word nano, which you may have stumbled already over when you read through the newspapers, and actually something which is associated with that small things are different. So before all that, a little bit on CRAN, which is the Center for Research on Adaptive Nanostructures and Nanodevices. It is indeed the first and the largest institute in Ireland, and this is now important, which is entirely dedicated to the research and the third level education in nanosciences, nanotechnologies, nanomaterials, right? So the only one in Ireland is here in Trinity College. It's on the Trinity campus. The building you may have passed by already is actually just on Pier Street, or Pier Street entrance of Trinity College. So, nano, well, a lot of words which you can see there: nanotechnology, nanometer, nanoscience, nanomedicine, nanobots, nanoelectronics, nanospintronics, etc., etc., etc. So the big question mark is, what is this all about, right? And bottom line is, you can summarize it into 3 words, okay? The first one is nano. It's simply a prefix which means small, right? So, and it comes from the Greek word nanos, which means as much as dwarf, dwarfish, or little old man. So, and it essentially means that if you put nano in front of something, then you take 1/1000th of that something you're looking at, right? That is when you put, that's the first step to understand all these nano words. Well, the other word is, sorry, nanoscience, right? And this is a part of science which focuses its studies on small things, right? We will see what small means. We're not yet there, but let's get step by step. So, and bottom line is, nanoscience is not really physics. It's not really chemistry. It's not really biology, right? In the classical sense, as you know it in your daily life. It's somehow all. And I will show you later why this is the case. And then there is the famous word nanotechnology, which is just the art and the science, right, of how to address or make materials on a nanometer scale, right, so that they're doing actually new things, things which they're not doing if they're large, okay? And this includes a lot of advances which are already existing in products which you buy nowadays and use in all possible industries: electronics, chemistry, pharmaceutical industry. All your smartphones, all your laptops, all these flat panel screens, etc., etc., wouldn't be able without nanoscience and nanotechnology. Pharmaceutical, the classical example, very prominent. I guess most of you have already used that product already, is sun cream. So in sun cream you actually have a lot of nanoparticles inside. The reason for that is because they are so small, they absorb the dangerous ultraviolet light much better than larger particles, right? So there's a full chain of things which we are going to go through a couple of more examples to demonstrate that this is really a huge thing of impact. So what is small? Let's start with this nice image here, right? It's a beautiful bush of roses, right? Imagine it smelling nice. Couldn't bring it here. So, and actually this distance here from left to right is approximately 1 meter. Now let's zoom in. Let's zoom in onto a leaf which was in the middle of this image. And we are now at some length scale of about 10 centimeters. Okay? And then we see, number one, the leaf has some structure. It's not just green. And specifically, we also see, well, there's even a fly sitting on top of that leaf. It looks pretty much the same. We see some shape, but, well, not too much structure. If we zoom in more, so to 1 centimeter, we see that actually a fly looks pretty interesting. There's a lot of different things attached, or which makes up a fly. Here you see the eyes, here the body, but the body is not continuously equal along its length, etc. Interesting. Let's zoom into that. 1 millimeter. And if you hadn't seen that image beforehand, and I would have just shown you that image, and I would have asked you, what is it? You probably would have been puzzled and would have guessed maybe some exotic fruit or something like that. But no, it's the eye of the fly, right? We're only at 1 millimeter and we see, wow, there's a lot of structure and a lot of things going on already on that scale. But we can go further. Again, 10 times smaller, 10 to the minus 4 meters, right? And what you see here is a zoom onto the eye of this fly, right? And you see that actually there's, again, even more structure appearing on that length scale, right? Now, we have made one little trick in going from the 1 millimeter to the 10 to the minus 4 millimeter. In the 1 millimeter case, we used an optical microscope, something which you have probably already used, which means where you simply have a lens, you shine light on your object, and the reflected light goes through the lens and gets magnified, so you can see things which are smaller. Now, this is so small that you just cannot use light anymore. Instead, what you have to use are electrons. But the principle is the same. You shoot electrons on the surface, they get reflected, and then through some special lens, you get a magnification. So this is how we can see 10 to the minus 4 meters. We can, of course, go further. 10 to the minus 5, which is zooming in one of these little, in between these little heaps. And there you see, well, still well structured, and even we have some little antennas at the cross-section of these 3 objects coming out. Right? Wow. So the smaller we get, the more structure we find. Right? Something which we don't see on the scale which we are used to from our daily life. And then we can even zoom further to 1 micrometer, so 10 to the minus 6 meters. And this is just the basically the root of this little antenna. And if you look careful, then you see, well, this little antenna actually has, again, structure. There is some structure. And even here you can see it, that the surface on which it's actually standing also has some structure. And then let's make a larger jump by 3 orders of magnitude, which means we go 1,000 times smaller than that. And what we would end up then is this, which you all probably have seen. This is DNA, right? The building block of life here on Earth, right? And the typical size of a DNA strand, as you have it here, this nice, beautiful double helix, is 2 nanometers, okay? We can push it even further and go to 0.1 nanometers, which is called an angstrom. And then we start to see, and this is the zoom in onto the DNA, then we start to see actually single atoms and how the individual atoms are actually arranged in such a way that they make up the DNA. So as a rule of thumb, you can say, well, 1 nanometer is approximately 10 atoms you're looking at. Okay? So if we talk about nanoscience and nanotechnology, then we're talking about doing science on a scale of a couple of atoms, can be also 100 atoms, but in any case, it's going to be like that, that if the position maybe of a single atom or of a few atoms is slightly changed, then the properties of that thing you're looking at, of that material, is changing, right? A little bit more philosophical, you can also say from our perspective, beings 1 to 2 meters in height. Well, if we look out to the stars, it looks infinitely large. But if we zoom in, we see it's also practically infinite, right? There's as much to be discovered on this small length scale. Okay, now, we know what is small. This is what, when we talk about it's small. But why is it different? Well, on such a small length scale, right, the laws of physics are different than the one in the macroscopic world, right? So, in your macroscopic world, you're used to the fact if you take an apple from a table, right, you remove it from the table and you lift it up. You don't hold it anymore, it's going to fall down. All these little bits and pieces. Now, that's macroscopic world, okay? So, and in this macroscopic world, you can divide, or you can do still this classical division of physics, chemistry, biology, talking about classical mechanics, classical electrodynamics, organic chemistry, inorganic chemistry, right? All these historical fields, right, which are existing. Now, if we get small, which means the microscopic world, along the lines what I just have presented, well then, this thing doesn't make sense anymore. And basically all what you do is you're doing science, okay? So, what's the reason for that? Well, on this small scale, the behavior of materials, of single atoms, molecules, etc., is determined by something which is called quantum mechanics. So, what's fancy about that? As I said, things get small, they don't behave anymore as they would if you are on a macroscopic scale. So take, for example, and this is something I hope everybody of you has done. If you take a ball, you have somewhere a wall, right? Then hopefully all of you have played this game of kicking this ball against this wall. So if you do that, it just bounces back, right? You can do that 100 times per day. You can continue your whole life doing that. It's always going to bounce back. So let's assume now you get really, really small, right? So you take yourself, you take the ball, you also take the ball, and you really shrink yourself down, right? Really, really small. Again, along the lines, what we have done there. Go from the size of the bush of roses down to DNA level or a couple of DNA strands. Well, then let's do the same again, right? Let's kick this ball against this wall, but we are now all small. What is going to happen? Well, you kick it, flies to the wall, but oops. Sometimes, not always, the ball doesn't get bounced back, but instead it tunnels through that wall. So suddenly you see it on the other side. This is something which I'm pretty sure nobody of you has seen in your daily life, right? So, where does this come from? Well, this is where, or this is a cornerstone of quantum mechanics. Because quantum mechanics says something quite weird, which says like every object, what you're looking at, if it's small enough, it is both at the same time. It's going to be a solid, but at the same time a wave, right? And by wave, just imagine the waves which you see on water when you throw, for example, a stone inside, right? And you all know that waves have different properties than a single, than a stone. But now, if you're small enough, then this distinction doesn't exist anymore. And actually, everything is both at the same time, has both properties. Okay? So, again, it's pretty weird. There's nobody in this world who really understands it. That's the reason why people are still working and trying to understand it. We are only, through nanotechnology and nanoscience, very recently actually, able to get much better understanding what is happening there. But because it's so weird, it's actually big fun to work on that, right? So only one example, there's a couple of others which are all associated with such things. Another thing which is associated with all that, if you go small enough, is a thing which is called quantization. And it basically tells you that you cannot infinitely shrink a certain material, right? So you can take your table at home, you can start to take, you can take an X and you can just try to make it smaller, 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 and smaller. You will have some success at the beginning, but at some stage, simply, you're going to reach a scale where things cannot get smaller. Now, nano is not yet the scale where that is, but it's already small enough where we can see effects of that. A very prominent example for that is the electric charge, which an object can carry. And the smallest one which you can have is the so-called charge quantum of about 1.602 times 10 to the minus ampere seconds, right? You cannot get smaller. That's simply how it is, right? So it's actually a fundamental constant of nature, right? And everybody who is doing science, no matter physics, chemistry, biology, needs to deal with that fact. So, how small do I need to get all that to happen? As I said already, you basically need to go to the nanometer scale. So, don't forget, a nanometer is just 10 to the minus 9 meters, 1 billionth of something. Now, a little bit of nanoscience, right? What is it? Well, it's studying, understanding what things materials do at the nanoscale, right? And just a currently strongly explored example is carbon, right? And you all know carbon from plants, and we also are made of carbon and a little bit of water and all this stuff. Now, if you take carbon, a carbon atom, right? Think about the DNA, there you had single atoms which were arranged in a specific way. If you can arrange carbon atoms also in different ways. In one way, it's graphite, right? So it's basically pencil lead, something which you can easily buy if you go in many shops, right? So, not a big deal. But if you arrange it differently, it's a diamond. This you cannot buy so easily, and usually you buy things like that if you want to impress your girlfriend. So same type of material, carbon, but simply arranging it on a nanometer scale differently makes completely two different things. This one here is soft, right? You can write on paper, you can break it easily. But if you take diamond, well, you are not going to write on paper, you can just scratch it. It's the hardest material known on this world, right? So, nano structure on the nanoscales plays a very important role. Now, let's zoom in with this fancy microscope which we have, which is not using light, but electrons, right? On this graphite thing, so the tip of this pencil. And if we zoom in, we see, well, it's not just grayish black. No, it has some structure. We zoom further in, it has even more structure. You start to see all these flakes and all this stuff. You can continue to zoom in, and then you're going to find out it's actually made of some layered material, right? Where you have a hexagonal arrangement of these carbon atoms. And actually what you see here is nothing else than a sheet of these carbon atoms, right? So all these bright spots which you have here are carbon atoms. So we are already today able, we do it actually routinely here in Trinity College, to see single carbon atoms. Of course, we can also see other elements, but this is where we are working in if we talk about nanoscience, nanotechnology. Now, just a little bit more on that. I gave you the example of graphite and of diamond. You can do more. You can take, for example, such a sheet of carbon atoms. You can roll it up into something which is called a nanotube, which has a diameter of about 1 nanometer. You can make little buckyballs, they are called, or fullerenes, which actually have the arrangement of the atoms is exactly the same one as you have on a soccer ball, right? And you can also make them in different sizes and actually put them like this Russian it together one into each other. Now the important thing to note is this you can do with material only on the nanoscale. Without going into detail, if you get larger, then the whole thing, right, such a tube would not be stable anymore energetically. It would just collapse. It would just flatten out. But if you get small enough, then you can start to have these type of structures, right? So one single element we're talking here about, and if you go to the nanoscale, you have a lot of possibilities how you can arrange it. Now, what are all of these guys doing? That's one of the questions we are asking ourselves when we are doing nanoscience. How are the electrical properties, magnetic properties, etc., etc., etc. So there is, of course, to understand these things, it's not only carbon, as I said. You have other materials. Here is controlled synthesis of, well, it's again carbon. Here another type of microscope, and you see these ripples, which are actually showing you also how each of the carbon atoms are arranged. Here, unfortunately, you cannot see it very well, but bottom line is this here is just a substrate, right? Silicon dioxide, on which we have put a single carbon nanotube, which you can hardly see. I apologize for that. And then we have put two electrodes on top of them, and we have measured the current through an object which has only 1 nanometer thickness, right? And the behavior is completely different than what you would expect from bulk electrical conductors. Now there are, of course, many other materials. Here we have a very nice image of the interface between iron oxide and magnesium oxide. Right here, this is all the atoms, all these bright dots are the atoms, the arrangement within the magnesium oxide. Here the iron oxide, and here you see the interface. Of course, there are other systems which you can grow synthetically. You have a cobalt core and the iron oxide shell, or here this is simply a germanium nanowire, approximately 30 nanometers in diameter, right? Span over 2 electrodes is freestanding. You can do all mechanical properties and electrical magnetic properties, etc., etc. And again, because it's nano, think about this nice example of the ball which tunnels through the wall. Well, because of these effects, the behavior of all these materials is quite different from that what we know on the macroscopic scale. Now, nanotechnology, let's take an example, electronics, because everybody of us is using it every day, right? And where we started off a couple of years, actually decades now ago, is microelectronics, right? And what has happened, we basically were able to shrink everything more and more down, right? Leading to that, as I said beforehand, smartphones, flat panel screens, etc. Nowadays, we are actually here in this area, right? Where we do nanoelectronics, where we make some structures which are actually a few or below 100 nanometers small, and we look how the electrical current is passing through these structures. Now, is that all just nice science, right? The crazy scientist in its lab playing around and being happy if something gets green or blue? No. Actually, and this is a colleague from Intel was giving me, the Intel Technology Roadmap. And what you see here are basically all just images of the transistors, right, which make out your processor in your smartphones, PCs, laptops, etc. Well, in 2003, the total size, if you want, or basically that size here, right, was 90 nanometers. Already quite small. Then 65, this is commercialized, of course, 65, right, nanometers in 2005. Then 45 nanometers, right, so this structure here, in 2007. 32 nanometers, 2009, right? And now we are 2011, plus more. And there we start to, sorry, I don't know why the image here is missing. And now we start to get into structures where actually we reach sizes of the order of 5 to 10 nanometers, right? So we're talking about structures which have a width of about 50 atoms. And we're looking how they behave, right? Actually, we have a couple here also in Trinity College, a large corporation with Intel Ireland and also Intel Portland in the US on that topic. So the progress here, which we see is, and this is important to note, is not just making things smaller, but really changing from one type of material, this here is basically silicon and germanium, right, to other types of material, because here now we have already the carbon nanotube. Okay? A lot of things needs to be understood still in this field, and this is why quite a lot of people are working in this area. Now, of course, the ultimate goal of nanotechnology is to take a single atom and to build something which, which you just have drawn on paper. And for example, you can do that with some effort if you evaporate or you deposit a couple of single atoms, for example, on a metal surface, a nice clean metal surface. These are these blobs which you can see, right? And you can start one by one actually building up a nice circle, right? Now, another thing which you will see here is in the middle is this ripples, right? Which remind you of something which is like a wave, right? Something which you see when you throw in a stone into water. Then you also get these type of ripples. And this is just what is happening here, because you're on this metal surface, you have a lot of electrons flying around, right? You know, metal is an electrical conductor. A lot of free electrons flying around, but we know from quantum mechanics they can also behave as waves. And this is what we see. So what we see here is nothing else than the wave character of electrons, right? So that's of course the ultimate goal. It's very difficult, right? Needs some effort, and but research is going on in this direction. So there's a lot of more stuff of this type, right? Than that, you have electronics, you have magnetism, you have spintronics, you have mechanical properties. All that can be investigated. All that is changing once you go small enough. So what else do you need to do all that? And what we have here in Trinity is, well, you need a lot of fancy looking machines. And unfortunately it looks like, because we have so big fingers, the smaller the things are we want to investigate, the larger the machines we need to build to actually be able to manipulate them. But what you see here is basically a microscope, right, which I was mentioning beforehand, which uses instead of light, electrons to make images. You can see it's a little bit larger than a simple optical microscope, because here's the screen of a normal screen of a computer. Well, there are other types of microscopes where you don't use electrons, but you use helium atoms. Same principle, right? But has some advantages. Of course, synthesis arrangements, other type of microscopes. And here what you see is basically, and this size here from here to there is just 3 millimeters. Unfortunately, you cannot see it very well. But here in the very middle is a little structure where you have a single carbon nanotube connected to 2 metallic leads, right, on the nanoscale. And we have just mounted that on some chip carrier, and through that we are able to measure the electrical properties of this material under many different conditions. What is happening if things are getting cold or warm? What is happening if you apply an additional electric field or a magnetic field, and so forth. So I invite you to check that out, right? Of course, on the Trinity College Physics webpage, also on the CRAN webpage, and also there's the Inspire Nano webpage, which is a national program which is there in order to promote nanoscience and nanotechnology, and also to increase the collaboration between people in Ireland, researchers in Ireland, working in this field. So, in some way, size matters. That's how it is. And if you have any more questions or do you want to know details, just drop me an email or an email to the School of Physics, physics@tct.ie. Thank you.